is Alistair McKee. I'm the engineering lead for analysis applications at Convergent, and today I'm going to give some examples of calibrating heat transfer coefficients using experimental data in Raven. Before we get into the case study, I'm going to give a little bit of background about thermal management of processing of composite parts and using a 1D thermal analysis in Raven. When we're producing composite parts, we actually need to take a look at the overall thermal system. In this case here, we're going to use an example of a tool with pre-preg as our part actually here, and then all of the consumables, the breather, release plies, vacuum bag, all of those are the materials that are going into our thermal system here. And as well, we need to take care of the boundary conditions. In this case, it could be an autoclave or an oven, and this is going to be used to apply heat or pressure or both. And that is what we are using to consolidate and cure the composite part to get the desired part out at the end. To calculate the temperature of the part during production, we could use this heat transfer equation to calculate the rate of change in internal energy of the part due to the conduction in the three different directions here, as well as the heat generation from the exothermic reaction during cure. And for that, we do need all of the density, heat capacity, conductivities of the materials that have gone in, plus the cure kinetics and relative volume fractions of the constituent materials as well. The other thing that comes into a simulation is then the boundary conditions. We can use different types of thermal boundary conditions in process simulation. Adiabatic, where there's no heat flow, or a set temperature, where actually we prescribe the boundary condition temperature. Radiation can be used, but convection is the most common one in autoclave and oven curing situations. So the equation here, the change in heat, the heat flux, is actually given here with this H, which is the heat transfer coefficient, the HTC, as well as the difference in air temperature to the part temperature. So the ways you can come up with this coefficient are through, for example, here we're showing computational fluid dynamics to actually calculate the fields of heat transfer as well as the airflow. We can experimentally measure these using heat flux sensors or calorimeters, or as we're going to show here, we can back calculate these using thermocouple data from parts. A convective HTC quantifies the heat transfer between a fluid and an object surface. HTC values will vary based on the surface or location within an autoclave, and this is because the theoretical HTC is dependent on the air velocity, pressure, and temperature, as well as whether or not it is laminar or turbulent airflow, and then the actual surface orientation and geometry of the parts itself and where it's located within the autoclave or oven. Now it's important to remember that what we're calculating is an effective HTC, and so this will lump in some other heat transfer mechanisms like radiation, and depending on where you calculate it, the conduction through the consumables, as well as contact resistances between different layers in the stack up. So it's important to remember that what we're calculating is an effective HTC, and this might vary, the actual magnitude might vary compared to a theoretically calculated value. When you need to estimate an HTC, a good place to start is with some typical values or established values under different flow conditions. And so as you can see here in this cross-section of the autoclave, we actually have a part representation in here as well. And we can see within this autoclave that we actually have areas with very low stagnant airflow. This would probably have a very low HTC, all the way up into these very high impinging zones where the part is actually not positioned, where we have very good airflow and very good heat transfer occurring. And that might be up at this value of, say, 100 watts per meter squared Kelvin. And in reality, we're most likely somewhere in between those. And ovens and autoclaves, they can overlap. Typically, though, an autoclave will give you a better HTC, which is one reason why they're used in industry. So the Raven 1D analysis is a good approximation for many composite parts. And this is because they're relatively thin and the in-plane conductivity is much, much higher typically than the through thickness conductivity. And that means that the through thickness direction becomes the limiting heat transfer direction in most parts. Now this is a good way to represent many different thicknesses of parts or thicknesses across a part. And what it's going to allow us by applying these heat transfer coefficients to this stack up is to calculate the thermal lag as well as the exotherm where the heat is generated by the part itself. The things we do have to keep in mind with the 1D analysis is that the assumption is that there is no heat transfer on the sides of the stack, which means that we're not getting edge effects. And so this is typically true for composites that are away when you're away from the edges. So if your thermocouple is right on the edge, you may or may not see some of the effect of this. And then the other limitation of Raven is that you can only apply a uniform HTC through the cycle rather than having it change throughout that cycle. Now you can define a different one on the top and bottom. However, if you move into Compro in a finite element package, you can actually have a HTC variable throughout a cycle. Now that some of the theoretical background has been covered, we're going to get into the case study where we back calculate the effective HTC values using Raven. The example case study we're going to use today is this large curved part. You can see it here in the autoclave. The airflow is back towards the page here, and you can see that it is on an aluminum tool. It's about 12 millimeters thick, and it was cured in the autoclave under a vacuum bag with breather. That's pretty typical conditions here, and is relatively thin. 16 plies gives us about 3 millimeters thick, using Toray 3900-2 with T800H fibers. In order to calculate the effective HTCs in this case, we're going to use production data. So some of the limitations of this is that they're typically a limited number of thermocouples. They're often located at the edge of the parts in the trim area, and they may be in the high or low airflow zones. They may not be moved around or located in several positions around the part. But I'm going to show you today how you can actually use this data anyway to calculate. So in my case here, we're looking at TC number 9 and 10. They're on this leading edge of the part here. And we're actually looking at, these are positioned right on the tool surface right below the part. So this is the location that we're actually going to calibrate to with our stack up. And we're going to move into Raven here and use the 1D analysis to actually back calculate the effective HTC for this position. I'm using version 3.12.12, and what I'm going to do is import the TC data. The data here was stored as a .csv with time in the first column and then temperature, pressure, vacuum levels all in the subsequent columns. I'm going to load all of the TC data here, and I'm going to use the default here, file name only. Now Raven does a pretty good job usually of picking up the data types, and so we can see here it's got time in minutes, and then we've got autoclave air temperature, as well as pressure, vacuum, and then all of the other part thermocouples. The data is in USCS here, so we've got degrees F, but I'm actually working in SI units, and so Raven has actually converted all of these here. So we'll do the rest of this in SI units. You'll see here right away, we see, well, this looks like we have a problem, but what it most likely is an errant thermocouple. This is pretty typical in production. TC5 looks like it's bad. I'm actually going to hide the series. And now everything starts to look a little bit more normal. Here we have a typical temperature profile of the part. We also have here autoclave pressure in pascals on this axis, and we've got the vacuum here. And I noticed that some of the axis here, it actually has the labeling, and so what I can do if I want to adjust that is just to delete that portion here by just simply double clicking on that portion. So we've got the vacuum on the inside axis here, we've got the pressure, the autoclave applied pressure here. Everything looks pretty normal. What I'm going to do is right click up here, and I can actually hide all the series, and then we're going to look at the air temperature as the input to this simulation, as well as the position 9 and 10. These were the ones we were going to look at first. And so this looks pretty normal. Those two track very close together, and this is because they're in a similar position in the part, and so this all makes sense. So what we want to do is run a simulation based on the air temperature and compare it to these real part temperatures. So to do so, I'm going to actually use the thermal profile, the 1D thermal profile study. This opens up here into the interface. I need to define a few things here. So first I'm going to do the boundary condition. And this is, as we've been talking about, it's the HTC here on the top. Now I'm going to define a material. In this case, we actually have some breather on top. I'm going to use the nominal breather. This is thermal properties only, 1 millimeter thickness. I'm going to use, I'm going to add another material here, and I'm going to use Torre 3900-2 and T800H fiber. This is a open material model, and we knew the part thickness to be 3 millimeters here. It's quite a thin part. And then we're actually going to add another material, and this is going to be the tooling. And so I'll select from here the tooling, aluminum, and this was 12.4 millimeters, that's about 1/2 inch. And below this now we're going to put the final boundary condition. This is the heat transfer coefficient on the bottom. And so we can see here now the full stack has been built. We have breather, curing composite, and then the tool material here. And the next thing we need to do is define a cycle. So I'll use the little ... here, and this is where we're going to actually use the cycle from data option. What I want to do is make sure that the source here is selected on the imported data. Great, that looks correct. And then the time here and temperature is the autoclave air TC. That's the one that we want to use, and we can use this option here to update the cycle when source data changes. Okay. This looks like the correct data here, and so I can go ahead and say OK. And then the next thing, or the last thing that I need to define before we run this simulation is what is the heat transfer coefficient. We're going to start with an initial guess, sort of middle of the road here for an autoclave process, 60 watts per meters squared Kelvin. And we're going to see how we do here. Raven will give you a warning if there aren't all of the materials in the stack up, if they do not have mechanical properties, it won't show any mechanical properties for any of them. So that's okay. That's fine. We're doing a thermal analysis here. And as this computes here, what we get is a thermal profile here with several different things shown. So I'm going to collapse our imported data plot here, and I'm going to look at this. I'm going to turn on the legend here, and we can move this down. And we can see here now what do we have in this stack up. We actually have several different materials. So we have the breather on top, we have the curing composite, and we have the tooling material here in the stack up. And by default, the 1D profile tool will actually create a top, middle, bottom for each one of those. So I'm going to go ahead and turn off the tooling and the breather, because we're not that interested in that. What we actually really wanted to know about was the composite, and we actually know that the TC was right at the bottom between the part and the tool, and so I'm going to turn off these two. And so this is the thermocouple that we, this the simulation that we want to match the thermocouple to. I can also turn off our HTC at the bottom because this is the same applied air temperature. So we have the input here, and then this is the portion that we want to match. So now I need to overlay the thermocouple data. To do so, I will right click and add a new series. I want to put this in its own group here. We see these are nicely categorized within different groups. I'm going to select this group here, and I'm going to call this TC data. Then I need to make sure that the source is correct. And so I'm actually going to click up here on the imported data. These are all the through thickness profiles, so we can select different things in the simulation if we want, but we want to actually compare to the incoming data. So here we go, and I want to make sure this is plotted on the same axis here, axis 1, and I actually want to plot a few points, so I'm going to select here, scrolling down, number 9 and 10. Okay, and so we've got time on the bottom axis. That's perfect. Go ahead. So now this is plotted here for us, our thermocouple data as well as our predicted data. And you can see we're not quite matching throughout the cycle, but it's in the right ballpark. So what we need to do here is actually we want to match as the composite is heating up. We want to match the properties here. This is going to be the uncured properties, thermal properties. We have the section here where the exotherm is occurring in the hold, and then we have the cool down, and this is the cured properties as well. So there's things that you can check all the way through the cycle. And we can see right away that the HTC that I've entered, 60, is actually a little bit low. And so what we want to do is potentially adjust that higher. So what I can do is open up this simulation here, and I can enter in a higher value as well. And we're going to see how this computes. Again, we get the warning about mechanical properties. And what we're actually trying to do is match these two together. And now what we can see is this is starting to look pretty good in this portion here. It's a little bit on the high side, but we're getting into the right kind of number. Now, some of you eagle eyes out there might have spotted that we're not matching in this zone. And actually, I want to focus in on here and talk a little bit about this. So two things I see right away that are going on here. One is that our actual part temperature was lower than the air temperature at the very start. And so the simulation actually starts from the defined air temperature. And so we have a discrepancy right from the beginning that we need to figure out a way around. So the workaround for this is that we're actually going to open our thermal profile. We're going to open the cycle from data and then come to this option here, edit cycle. Within this is actually our tabular value here, and I can actually put in that value here, and I know that this is about 24 degrees actually. And so I can actually enter that directly in, and what this does is for the very first time step, fixes that point down here at 24 degrees, which is going to match everything together. And so I'm going to go ahead and click OK. So this simulation is going to rerun, and what we'll see is that we now match here. And so that is very helpful because we want to match up as we come along here. You can actually probe and get the exact temperature if you want in that particular case. Now, we also see a little bit of a variation through here, but we see this something with the air temperature. And so I'm going to jump back here to the original data and turn on the autoclave pressure. And we see that this air temperature here is adjusting, and it is adjusting, most likely the controller on the autoclave is adjusting based on the pressurization. And we know that the heat transfer coefficient is actually dependent on the pressure. And so this zone up to about 10 minutes here, if I probe this, we see that the pressure is changing, and therefore the HTC is likely changing as well. Now we're probably relatively constant for the rest of the cycle. Unfortunately, Raven does not have the option to put in variable heat transfer coefficients. And so we aren't able to vary it through here. So what we're going to do actually in this case is ignore this zone here, but we know why this is happening. And what we're going to focus on is the rest here. And so, as I said, we were matching pretty close at 100 watts per meter squared Kelvin here, but we are still actually a little bit high, and so I'm going to come in and adjust this down slightly. We started with 60, that was too low, 100 was too high. I'm going to come in here at about 85, and we'll compute here, and we're actually seeing if we can get this to match up a little better. And now that looks quite good. We're right in the middle of those two temperatures, and so I'd say that's well within the experimental error. We see we're very good on the heat up. We see we're quite good, a little bit off on the cool down. And then the other area that we're of interest here is the exotherm during the hold. You might say, okay, well, why aren't we matching here as well? And so that's a good question. So if we look at this here, the simulation is predicting a slight exotherm above the hold temperature. It's about 183 degrees Celsius, and there's a slight peak here at about 185 predicted by the model. Now, what we have to do is remember that the assumptions that we've made in this type of analysis. So this is a 1D thermal profile, and this is valid in the middle of parts usually, away from the edges. Now we actually know in reality that these thermocouples are right at the edge of this part. And so very likely there is some heat transfer occurring out the edge of the part, and that's why we see no exotherm essentially within these parts, is that there is actually some heat transfer conducting away from these thermocouples out the edge. So if you wanted to capture this quite well, you would want to go in and actually potentially move to a 2D or 3D Compro simulation, which would be able to capture those edge effects. The other thing to point out here, though, is the accuracy of the data that we're capturing here. And what we see here is that the air temperature, by the end of this hold, I would expect the air, the part, the tool, all to be very isothermal, essentially the same temperature here. But what we actually see is that these all come to different temperatures, and the difference between all of these is around 2 degrees, and that's about the error that we're seeing here as well. So sometimes it's worth keeping these things in perspective as well. So for TC 9 and 10, we came up with a calibrated effective HTC of 85 watts per meter squared Kelvin. Now, this does come in actually quite high on the typical values, and when we actually look at the positioning here, the airflow is coming in directly at this, and so this actually does make sense. This is the air coming right initially in onto this part. It's also coming through the under side here and probably blowing directly on this position at 9 and 10. And so this does make sense. We're going to see a relatively high HTC here, and we do get a relatively good match all the way through this cycle. Now we can look at another position on the part at TC 1 and 2. These are located on the back side of the part here. This is a bit shielded from the airflow, and so we might actually see a different effective HTC there. These positions similarly have a thermocouple located right between the part and the tool. And so we're going to swap back into Raven and see how we would calibrate for this position. So now we're going to look at position 1 and 2, TC 1 and 2 in this part, and see if we can calibrate the HTC for that position as well, and see how much it changes compared to where we were before. So first thing I'm going to do is add these to this plot. So I'm going to right click, new series, and I'm going to select the source here as the imported data. Okay. I'm going to make sure that I am on the same axis here, and then I want to actually select multiple temperature profiles here, so these TC1 and 2, which I use the little dot menu, and then the last thing I'm going to do is make sure that I group these with my other TC data in the series group here, so that's going to show up down in here. That just keeps things organized in the tree. I'm going to hit OK, and so the very first thing that I see here now is that these TCs do actually lag behind these other ones, and that makes sense with their position within the autoclave. They're actually on the backside there with a little bit of shielding for the airflow, and so this makes sense. So these are probably going to be a lower value than what we had before. There's also a little bit more spatial variation, and again, this is real. This is the experiment in this case, and so we're actually going to probably try to get a value right in the middle of these. And so for now, I'm going to actually hide my TC 9 and 10. And now what we need to do is calibrate this effective HTC to match up with these parts here. So I'm going to go back to the default that we had started with, 60 watts per meter squared Kelvin. OK. And as this calculates here, we're going to see if this kind of brings it down into the reasonable level here. And what we see actually now, this is actually still a little bit high. And so then to continue with the same process, we're actually going to choose something a little bit lower here, 30. This is on the low end of the default values. We're going to say OK. And we can see here now this will compute, and it's actually a little bit too low. And so we know now that the HTC is somewhere in between 30 and 60. And so I'm actually going to come in here because I have done this before, and I'm going to come into a value of 43. So it actually is about in the middle of that, but it's been calibrated again, zeroed in on this. And because these simulations are so quick, you can actually zero in on these quite quickly. And we can zoom in here. I've got it right in between these two thermocouples. So this would be a reasonable assumption for that location. Again, we do see a very slight variation in the exotherm. Now this, that we don't quite see it in the parts, whereas we do see this in the simulation. This again could be because we're near the edges of this part. And again, on the cool down, it looks quite reasonable here. Not quite perfect, and you know, this could be due to the material property models, experimental error, or various things that the HTC could even be changing on the cool down. So for TC1 and 2, we came up with a calibrated effective HTC of 43 watts per meter squared Kelvin. And this is a lower value than we saw on the leading edge of the part. And this is actually consistent given the position at the back of the autoclave in a relatively low airflow zone. Now what's important to see is that we do see these variations on the parts, and so calculating a local HTC is important for the most accurate results. And what you can also do with this is that you can bound a problem by capturing the areas with the lowest and the highest HTCs, and now you know that you can simulate other positions in here within that bound. In the previous examples, we were looking at a single thermocouple through the thickness. However, if you set out to design an experiment where you would actually like to increase the fidelity of these heat transfer coefficients that you can calculate, you can add additional thermocouples through the thickness, and this can be through the part. So in this example, we're going to have a thermocouple on the top and bottom of the part, as well as adding a local air temperature just above the bag in this case. And this is going to give us some information about the gradients observed through the part and allow us to actually fine tune those HTCs at the top and bottom of the part. Now we're going to look at position 6, where we actually have multiple thermocouples. We have a local air temperature plus a thermocouple on the top and bottom of the laminate. So what I need to do, like I have done before, is add these series here. And so first I'm going to actually make sure that I have the correct source. I'm going to make sure that these are going into TC data, the grouping here, and then I'm going to make sure these are on the same axis. I want to select multiples here, so I'll turn off the autoclave air temperature, but I'm going to turn on TC6, 6.1, and 6.2. And then for some slightly better contrast, I'm going to select a different color. This will rotate through the colors as the data source changes. That's as the TC changes. And so now we can see here that these have been plotted on here, and actually I can see right away the local air temperature, which is the yellow line here, 6.2, TC 6.2, is matching actually quite close to the air temperature, which means the local air temperature there is being captured rather nicely by the autoclave air temperature. So that's a good sign there. However, we can actually use this as the input for our simulation. And then we also have here the top of the laminate and bottom of the laminate, where previously we only had the bottom of the laminate. So I'm going to go ahead and turn off TC1 and 2 there for a little bit more clarity. In fact, we can even turn, well, we're going to edit the HTC here at the top to run off of this other data source. And so what we need to do now is go into our profile here and adjust the input source data here. So I'm going to come in here and select the imported data, and instead of autoclave air TC, we're actually going to use that was 6.2 as the incoming one. Looks nearly identical, but it is the local air temperature. I'm going to go back to my default here as well, 60 and 60, just as a starting point, and then we're going to click OK. Okay, so you can see that the actual input, the HTC value, the boundary condition has matched now with this, which is good. That's what we wanted, and we're actually pretty close in terms of this. Now, the other thing that we can do here now is we can look at both the top of the laminate and the bottom of the laminate. So I'm going to turn on that top of the laminate, and then we're going to need to zoom in here a little bit to see a bit better definition between these. I'll move this out of the way, and we can see here that at this value here is 60 watts per meter squared Kelvin. We're pretty close on the bottom, but it seems like we're lagging behind, so it's probably a little bit low for the top compared to the actual TC data here at position 6. So what we're going to do now is adjust these independent of each other and see if we can bring this one up. So I'm going to try a little bit higher, and because I think I can do slightly better on the bottom, I actually am going to lower that just ever so slightly here down to 55. I'm going to hit OK. And so what we're trying to do is now match the spread or the gradient that we see at this position here to try to match these up a little bit closer throughout the cycle. I'm going to zoom in here again. You can see that we're reasonably close on the bottom, but still a little bit low on the top. And so then I can come back in here and adjust this one independently as well. I'm going to go up to about 85 here. See, this is similar to the position that we saw in 9 and 10, TC 9 and 10, and so I'm hoping this will bring it up here. Now we do see that it's not perfect all the way through, but this is the idea that we would have here where we can try to match the top and bottom all the way through that cycle. We can see here again there's a bit of variation in the thermocouple inputs, and so I think we're well within the accuracy of these thermocouples. And on the cool down, still not perfect, but still pretty close trending. So now we see at position 6, which is located about the midpoint of the part, where we actually had multiple TCs to calibrate with. We came up with a top value of 85 watts per meter squared Kelvin and a bottom value of 55 watts per meter squared Kelvin. And what's interesting about this is that it is somewhat in between what we saw at TC 9 and 10, and then compared to TC 1 and 2 at the back end of that. And what is nice is that we're also seeing in this position that we're bounded by a very similar range of values here. And this is nice because we're actually able to calculate then that top and bottom and further refine our inputs for as boundary conditions here. Through those examples, we were actually able to see that the HTC is dependent on the airflow and location in the autoclave. We saw the highest value at TC 9 and 10, as well as the top of TC position 6. And we saw the lower value on the underside there, which is consistent with the airflow and the positioning here. We'd expect stagnant airflow here. And on the back side of the part as well, at position 1 and 2, we saw the lowest value. Now, at position 6, we had additional TCs, and this allowed for a more detailed analysis and calibration of those effective HTC values. And so in summary, we built up a table of values here, and this can be very powerful and important for bounding your problem, because now we actually have a range for this quite large part that we would want to check in terms of compliance to a specification. Now we have essentially bounded the problem of what are the inputs we need to check from 43 watts per meter squared Kelvin all the way up to 85. And this is the power with simulation, is that we're actually able to now quantify those values. Through these examples, we were able to see that the HTC boundary condition allows you to account for thermal lag between the air, the part, tool temperatures, and the Raven 1D drill-through analysis can be used to actually calculate gradients through the thickness of that part as well. And we were able to back calculate effective heat transfer coefficients by comparing real experimental data to the simulation at the same location. And Raven was able to quickly import that experimental data to compare to these simulations. And as a result, we did see a lot of spatial variations throughout the oven and or autoclave, and this can be very important for bounding your thermal management problem. In conclusion, we saw today that Raven can be used to quickly analyze composite parts and compare these to thermocouple or other data. It can be a powerful tool for doing sensitivity analysis and to bound these heat transfer problems. And the effective HTC values can be calibrated in Raven and then used as inputs into 3D simulations with Compro, for example.